All right, well, we have our contextual applications of integration, pretty much our related rates and other nightmare section. Let's get into it. A person is standing 10 meters east of an intersection. So they are standing, and a car is driving towards them from the north. I'm going to do an arrow for the motion at 13 meters a second. And then it says at a certain instant the car is 24 meters from the intersection. And what is the rate of change of the distance between the car and the person in that instant? And so we are essentially looking for that rate, right? How much is that bar directly connecting them essentially decreasing? So here we go. The idea behind this problem is we're looking at a Pythagorean theorem question, and we know that the person is 10 meters away. We know the car is 24 meters from the intersection, and so we're going to have to do the Pythagorean theorem to figure out what the hypotenuse is at that moment. And there we go. 26 away. That is the current distance away, but we don't want to know the current distance away. We want to know how that distance is changing over time. And so what we have to do is we have to set up the Pythagorean theorem. And so what I'm going to do is I'm going to call x the horizontal distance, and y the vertical distance, and z the distance in between. And here is the trick to this problem. We need to derive this with respect to time to figure out how things are changing. The big trick here is that x is a constant. This person is not moving. So when I derive x squared, that actually just derives to 0. When I derive y squared, y, the vertical distance, is in motion. So what I'm going to get is I'm going to get 2y dy dt. And then same thing for z, because z is the distance in between the two, that is in motion, so I'll get a 2z dz dt. And so from there, let's see here, we do know what y currently is. The vertical distance at the moment is 24, and that's being multiplied by how the vertical distance is changing. And since it's moving towards, this vertical distance is getting smaller, which means it's actually negative 13. That's the key to getting this question right. From there, 2 times the current distance of z, which is 26, and dz dt is the value we're trying to solve for. So all we have to do is multiply all these together and divide by 2 and 26. And it looks like if you do that, you're going to get negative 12, because the 2's will cancel, and then there will be, the 26 has 2 13s in it, so we have negative 2 on the bottom, and then we have 24, so yeah, negative 12 meters a second. All right, Steve was given this problem, so were we. The radius r of t of a circle is increasing at a rate of 3 centimeters a second. At a certain instant, the radius is 8 centimeters. At what rate is the area of the circle changing, and how should we solve this equation? Well, if we want to know how the circle area is changing, then we're going to need to start with the circle formula. Right, up next, the side of the base of a square prism is decreasing at a rate of 7 kilometers per minute, and the height of the prism is increasing at a rate of 10 kilometers per minute. At a certain instant, the base side is 4 and the height is 9. What is the rate of change in the surface area? So first, let's kind of get a 3D drawing of this picture. Better me would pause this video, but remember that this is a square base. Not even doing this nicely, but oh gosh. Again, imagine a perfectly square base. All right, so what that means is when they said at a certain instance the base's side is 4, that means this is 4 and this is 4, and the height is 9, hooray. But the idea is that the base is decreasing at a rate, so in other words the change in base over time is decreasing at 7 kilometers per minute. the change in height over time is actually increasing at a rate of 10. So decreasing gets a negative, increasing gets a positive, and we want to know the change in surface area here. Let me quickly draw what we call the net of this object. So you can see if I unfolded this whole thing, I would have those two squares, and I would have four. These each should be the same width. I'm just not good at drawing because they came from a square base. So each of these are the same width. But anyways, that's the net. We want to know the change in the surface area, so how could we write the formula for the surface area? Well, the surface area is 2 squares, so 2 of that base value squared, because that's the area formula for a squared, just the side length squared, so 2 squares, plus 4 rectangles that have the base and the height. There's our surface area formula. And now we're going to find the rate of change in the surface area formula. Maybe I'll just call it S instead of writing DSA. And when I derive that, I'll get 4b and then a dB dt, because we're deriving with respect to time, not with respect to b or h. Then I'll have a plus 4, and now I have a product rule. So I get dB dt and keep the h, and then I get a keep the b and dH dt. So now we have to do a lot of substituting. We know b is 4, we know h is 9, we know dB dt is -7, we know dH dt is 10, so here goes nothing. 4b is really going to be 4 times 4 times -7 plus 4, and dB dt is again -7. H was currently 9, b was currently 4, and dH dt was 10. So we have 16 times -7 plus, I'm going to write it like this maybe to be fancy, 36 times -7 plus 160. So if we have 16 negative 7s and we have 36 negative 7s, we really have 52 negative 7s. Maybe that helps us do the math, maybe it really doesn't. And then we have to add 360, and so it looks like the surface area is decreasing by -204 square kilograms per minute. Alright, up next, an object is moving along the line, a line. The following graph gives an object's position relative to its starting point, and we need to figure out whether the graph is moving forward, backward, or neither. And so the idea is, if an object is moving forward, then, let me see here, then its velocity should be positive, right? And if an object is moving backward, its velocity should be negative. And since we're looking at position, we need to be thinking about the derivative of position, because the derivative of position is velocity. And just in general, it's worth writing down that position derives to velocity, and velocity derives to acceleration. Now what's not covered on the AP exam again this year is doing integrals with this, but just remember that it goes P, then V, then A, but if you were integrating, even though it's not on the exam this year, you would integrate A and get back to V plus a C, and if you integrated V, you would get back to P, and you'd have to add a different C. But again, that's not on the AP exam this year. Anyways, so where is the velocity? If we want to know where it's moving forward, it's where's the derivative positive, where is it moving backward, where the derivative is negative, or is it neither, when the derivative is 0. So negative derivative, moving backward, negative velocity. This is neither because the derivative is 0. This is moving forward, the derivative is positive, and this is neither because the derivative is 0. Right? Up next, more related rates. Goodness. The circumference of a circle, so I'm going to call that d capital C dt, is increasing at a rate of pi over 2, so positive pi over 2. And then at a certain instance, the circumference is 12 pi. And this time the question is, what is dA dt, the change in the area? So the idea is, if we want to know what dA dt is, we want to start by saying, well, what is just the area of the circle? And that's pi r squared. Well, from there, that means dA dt is deriving, we'll end up with a 2 pi r, so we'll drop the 2 down, I'll just stick it in front of the pi, and then we'll also get a dr dt. So the idea of this problem, the whole, problem of this problem is we need to know r and we need to know dr dt, but all they told us was information about the circumference. But the good news is the circumference formula involves r, so we'll be able to find r in dr dt. First thing we can do is easily find r, because if 2 pi r is c, and c is 12 pi, we'll just substitute that in. 12 pi is 2 pi r, we'll divide 2 pi, and you'll know r is 6. Now I'm going fast through some of this, but hopefully this is just review. From there, we need to derive this formula for circumference, so dc dt equals 2 pi, and then I'll have a 1 dr dt. And the idea was this was equal to pi over 2. And so when you divide 2 pi, you'll end up getting, multiplied by, not equal to. So when you divide 2 pi, you'll end up saying that dr dt is equal to 1/4. The pi's will cancel, now you have a 2 and a 2 on the bottom, so you have 1/4 at the bottom. So cool, now we know that r is 6, we know dr dt is 1/4. Let's plug all that in and we'll know the change in area. So we have 2 times pi times 6 times 1/4, and that ends up simplifying to 3 pi. All right. Herman is riding his hoverboard. Look at them trying to be hip with the kids. The function v gives Herman's velocity in t seconds after he starts riding. What is the best interpretation for the following statement? The value of the derivative of v at t equals 5 is equal to 1.5. So if we derive v, remember what I just said, v derives to acceleration. So the value of the derivative at 5 is actually telling you the acceleration at 5. And again, notice what I said there, it's the acceleration at 5. So that means answer choice A is out because it's saying during the first 5, and no, it's not during the first 5, it's at first 5, or at 5. So after 5 seconds, in other words, at the moment that 5 seconds have passed, Herman's acceleration is 1.5. And here's the thing about meter or acceleration, it's always your time unit squared. So velocity is always written as meters per second, but acceleration is written as meters per second squared if you're dealing with meters in seconds. In other words, velocity is just the distance divided by time, and acceleration is the distance divided by time squared. All right, got about time for one more before I have to cut this video off and go to a second. And of course, it's another ugly word problem. The length m of t of a rhombus says diagonal is decreasing at a rate of 3 centimeters per hour, and the length n of t of the other diagonal is increasing at a rate of 11 centimeters per hour. At a certain instance, time equals 0. The decreasing diagonal is 5, and the increasing diagonal is 5. What is the rate of change in the area? Match each expression with its units. Well, they already told me m of t, the length m of t. Well, they told me how m of t is decreasing and it's 3 centimeters an hour, so the key is, well, m of t must just be in centimeters because that's just the length itself. So m of t is just the length, just the centimeters. N prime of t. N prime of t equals 0 is actually this sentence right here. All right, so if we derive n prime, they're telling us n prime of t is always 11 centimeters per hour. So n prime at t equals 0, or really n prime of anywhere, is going to be given in centimeters an hour. And last but not least, what is the rate of change in the area? That's what we're looking for, but notice this is just the area formula itself, and an area formula itself is units squared. This is not a prime of t. If it was a prime of t, we would choose this box.